An equilateral triangle and a square are inscribed in the same circle in such a way that no vertices of the triangle and square coincide. Show that amongst the 7 circular arcs thus obtained, there will always be one which is not longer than 1/24 of the circumference of the circle. So, a question like this, where I'm trying to show that something is no more than something else, or the distance between two things is less than a certain amount, it really suggests that this is a pigeonhole principle kind of question. So this phrase here is not longer than 1/24 of the circumference. That's really suggesting to me that this is a pigeonhole principle question. And given that there is a geometric component to this question, it's a very good idea to have a diagram that you can look at and investigate to see how you can set up your pigeonhole principle. So I'm going to add in a circle with an equilateral triangle and a square. And we should also have a look at what this looks like when they are in the configuration that's described in the question. Namely that this triangle is inscribed inside the circle, along with the square being inscribed inside, but none of the vertices are overlapping. And so this is the shape that we get. This is the configuration. And you can see that, as the question even tells us, there are 7 circular arcs that are obtained. So we have 1, 2, 3, 4 in there, 5, another small one, 6, and 7 altogether. So now that we have a feel of how the question looks, or how the geometrical configuration looks, now we have to work out how we're going to apply the pigeonhole principle here. And we know that with the pigeonhole principle, we need there to be more pigeons than there are pigeonholes. So we have to keep that in mind as we're going through and attempting a pigeonhole principle question. So I'm actually going to take out these shapes. I'm going to put them back outside of the circle, because as we're going through and doing the question, I want to move the shapes in order to visualize what's going on. Now, the first thing that I'm going to do, given that I need to refer to the circumference of the circle throughout my solution, or at least once in my solution, I don't want to have to write that out a lot of times. So I'm going to give it a label. I'm just going to say, let L be the circumference of the circle. So now that I have a label for it, it just saves me a bit of time. And also I'm going to be dealing with these shapes and some arcs. So I need to be able to label those as well. So I'm going to label the vertices of my triangle and of my square. So I'm going to call the triangle ABC, and the square I'll call PQRS. And that's also going to be something advantageous for me as well. Now, remember we said that we want to think about how we can apply the pigeonhole principle. And with the pigeonhole principle, we need to have more pigeons than we have pigeonholes. So for example, if I had 3 holes, I need to have 4 or more pigeons. And in this case, the way that I'm going to set this up is I'm first going to add the triangle in. So the triangle is going to be the first shape that I take and inscribe inside of my circle. So I'll do something like this. And you can see that as I add in my equilateral triangle, it splits the circumference into 3 equal circle arcs. So we're going to have 3 arc lengths that are each L on 3 in length. And these arc lengths are actually going to play the role of my pigeonholes. And then my pigeons are going to be the things that I place on these arc lengths. And they are going to come from the square's vertices. So I have 4 square vertices, and they're going to be placed in my 3 arc lengths. 4 pigeons, 3 pigeonholes. And that allows me to make use of the pigeonhole principle. So I need to describe this in some way as I'm doing my solution, because most of my solution is an explanation rather than some complicated mathematical equation. So let me write out my explanation and we'll go through it together. So the first part is to fix the vertices of triangle ABC within the circle, and then the vertices form 3 arc lengths, AB, BC, and CA, which gives us that each of those arc lengths is each equal to L divided by 3, the circumference divided by 3. Now what we're going to do is we're going to take this square and inscribe it within the circle. And what you'll notice happens as we do this is that the four vertices of the square, P, Q, R, and S, are now sitting on one of the three arcs that were formed from the equilateral triangle. So I've got four items, four pigeons being placed in three pigeonholes, those pigeonholes being the arcs that were formed from the equilateral triangle. And this is where the pigeonhole principle comes into play, because the pigeonhole principle will guarantee that at least one of those arcs has at least two of the vertices of the square. And we can see that in the diagram we've drawn, it's the arc AB, which has at least two vertices, which are the vertices P and Q. And so this is now what I need to describe using words in my solution. So let's go ahead and write that out. So by the pigeonhole principle, with the holes equal to the three arcs, AB, BC, and CA, and the pigeons being the four vertices of the square, P, Q, R, and S, there is at least one arc with at least two vertices on it. Now, we need to pick the letters that we're going to use. And in the configuration that we've got up here, the letters are the vertices P and Q. But I could have relabeled these. These could have been R and S. So what we say in this situation is without loss of generality, because we're specifying that we're talking about the vertices P and Q, but we haven't lost the generality, because the generality can be obtained by just renaming or relabeling these vertices. So this is what you may sometimes see abbreviated as WLOG. So without loss of generality, suppose that, let's say, P and Q lie on arc AB. Okay, what can we say from here? Well, if we go back up to the diagram, remember we have to talk about one of the 7 arc lengths being less than 1/24th of the entire circumference. So let's consider this arc length AB, from A all the way around to B. Now that can be broken up into 3 other arc lengths. That's AP plus PQ plus QB. So I'm going to state that. Now the reason I'm specifying arc each time is because generally, if I just said AB, that refers to the straight line segment between A and B. So I'm going to be very specific and say that we're talking about the arc AB. Now, what do I know about these? Well, I know that arc AB from the very first part of the solution, that's equal to L on 3. And so now I'm starting to introduce the circumference into my solution. So this is equal to arc AP. But what about arc PQ? Arc PQ is formed from just placing the square, and these vertices of the square, these would divide the circle into 4 equal parts. So actually arc PQ, that would be 1/4 of the total circumference of the circle. So this is going to be equal to L on 4. And then I still have arc QB. So if I move the L on 4 to the other side, I have L on 3 minus L on 4, that's L on 12, equal to arc AP plus arc QB. And here I'm basically done, because whichever of these two is smaller, and we don't know which that is, that could be either of them, but whichever of these is smaller, it can't be larger than 1/2 of this. Because if it was, then I'd have the smaller one more than 1/2, and that means the larger one also has to be more than 1/2 by virtue of being larger than the smaller one. So this or this, one of them, has to be smaller than L on 12 divided by 2. So I'll say, therefore, the smaller of arc AP and arc QB has to be less than or equal to 1/2 times L on 12, which is 1 on 24 lots of L. And I'm not trying to prove that there's a specific arc which is less than 1/24 of the circumference. I'm just trying to prove that there's an arc that exists which is less than or equal to 1/24 of L. And that does it right there. I'm not specifying which one it is, I'm just saying that one of them is, and so I'm showing the existence of such an arc. And that's the end of our question.